Welcome back from that short little break. It's time now to delve deeper into electromagnetic radiation. We're now going to take a closer look at the wave equation and how it applies specifically to electromagnetic radiation. And later, we're going to have a look at how electromagnetic radiation propagates. So let's head to our concept map. We've been unpacking electromagnetic radiation. As before, we have looked at the properties that it exhibits like waves. We've looked at the properties of particles that it exhibits. It's now time to bring in this idea of how fast the wave is traveling and how it propagates through space. So let's have a look at the wave equation. In the wave equation, we already know that you can calculate the velocity of a wave in meters per second by taking the product of the frequency of the wave, which is measured in hertz, and its wavelength, which is measured in meters. But electromagnetic radiation is quite unique, and for that reason, we have to modify the wave equation so that it makes sense in terms of electromagnetic radiation. So how are we going to do that? Let's have a look. As I said, electromagnetic radiation is quite unique in terms of waves. In fact, it travels faster than anything else in the entire universe. In fact, we are pretty sure that the speed that electromagnetic radiation travels at is as fast as anything can go. Interestingly, and part of why electromagnetic radiation is so unique, is that the wave speed for electromagnetic radiation is the same as long as the electromagnetic radiation is passing through a vacuum. Therefore, all electromagnetic radiation, when passing through a vacuum, travels at the same speed. This speed is quite important, and so it receives its own symbol, c. c is equal to 3 times 10 to the power of 8 meters per second. C is a very important variable in physics, not just for waves. You may have encountered it even in one of the most famous physics equations ever, Einstein's own E equals mc squared. That c you see there is the exact same c that we are referring to, the speed of light. So how fast is that? I mean, it seems pretty big a number, right? It's got 8 zeros after that 3. I mean, think about it. When you're driving on the road in a suburban area, you're only doing 60 kilometers per hour. So how fast is light in comparison to that? Let's have a look. We've already said that c is the symbol for the speed of light. But if we convert it from meters per second to kilometers per second, we can see that it's a huge amount, 300,000 kilometers per second. Significantly faster than you would go on the highway even. Significantly faster than any of us will ever go. This is why you'll never see light traveling. It's just too fast. Have you ever noticed that when you turn on the light in your room, you never catch the light traveling across the room? The room is either dark or then instantly lit. The reason for this is that the speed of light is just way too fast for us to see. Our eyes are just not geared to be able to see the light or the wave moving through the air as it goes. So let's have a look at some questions to get our heads around the numbers associated with the speed of light. So our question here is, how long does it take for the sun's electromagnetic radiation to reach the Earth? To do this calculation, we have to A, know the speed of light, which we've been given, and B, we need to know just how far the sun is from the Earth. Now this number is quite big. It might surprise you. The sun is 150.38 million kilometers away from the Earth. So how long does it take this super fast light to reach us? So to begin, we need to list all of our variables. We have the speed, 3 times 10 to the power of 8 meters per second. Now remember that it's in meters per second, so we're going to have to convert any other units that involve distance to meters as well. We also have the distance that we mentioned earlier, 150.38 million kilometers. We're going to have to convert this into meters. So this converted into meters will be 150.38 times 10 to the power of 9 meters, because we are converting first the million phrase to scientific notation, which is 10 to the power of 6, and then we are converting the kilometers to meters, and there are obviously 1,000 meters in a kilometer, so it's another 10 to the 3, which gives us 150.38 times 10 to the 9 meters. Now we're looking for the time, so we're going to have to use our formula. We know that speed is equal to distance over time. So to begin, we need to fill in the variables we do have and then rearrange the formula to be able to get what we need. So the speed is 3 times 10 to the power of 8 meters per second. And this will be equal to our 150.38 times 10 to the power of 9 meters, all divided by our time value, t, that we need. So to get the answer, we're going to multiply both sides of the equation by t, and then divide both sides of the equation by the speed of light. This will give us that t is equal to 150.38 times 10 to the power of 9, must still include our scientific notation in the calculation, divided by 3 times 10 to the power of 8. So, definitely can't do that in our head. So to the calculator we go. We have 150.38, forgot my brackets, let's put the brackets in there, 150.38 times 10 to the power of 9, all divided by 3 times 10 to the power of 8, close the bracket, hit equals, and then convert it. We get that our time value is approximately 501 seconds. 501 seconds? That doesn't seem that much, or does it? I suppose if you think about the distance that we're talking about here, literally millions of kilometers, then that time doesn't seem that bad, does it? Can we expand on this idea? Let's have a look. If the time is only 501 seconds to travel that huge distance, how much is that in minutes? Well, that means if we convert 501 seconds to minutes, we get that this is approximately 8.3 minutes. i.e., it takes light approximately 8.3 minutes to get from the sun to us. We often refer to this unit just as that, a light minute, the distance that light travels in a single minute. It's quite a distance, but we use it a lot in physics. A term you may have heard used more in physics is perhaps a light year. Have you heard of a light year before? When people talk about light years in movies, do they usually refer to a period of time or a distance? Well, you'll often find that if the movie was made by someone who understands science, light year will be used correctly to describe a very large distance, i.e. the distance that light would travel in a single year. If they're not very clued up on science, they tend to use the term light year to describe an amount of time, which it is not. And so that's a nice example of how some people who don't understand science as well as we do tend to make silly mistakes in their use of the terminology. This term, a light year, how far is that distance? Can we do that calculation as well? Absolutely we can. Let's have a look. So we already know that light travels at 3 times 10 to the power of 8 meters per second in a vacuum. And with a quick bit of math, I was able to determine that there are 3.154 times 10 to the 7 seconds in a single year. Therefore, if we use our formula, but just rearranged from the previous slide, we can get that distance is equal to speed multiplied by time. And when we multiply the speed of light by the number of seconds in a year, we get that the distance of a single light year is 9.461 times 10 to the power of 15 meters. A truly colossal distance, far, far longer a distance than the distance between our Earth and the Sun. All right, so now we've come to the end of the section. Let's take a short break, and when we come back, we can have a look at how electromagnetic waves propagate through space.